Hello, my name is Pratik Tolambia. I have done my mechanical engineering from NIT Raipur and currently I am working at Sense as a facility technologist in the lithography bay. So today I will be discussing about the lithography introduction or the basics of lithography. What is lithography basically? So lithography is just transfer of pattern from one place to another place, or basically you can say just transferring the patterns from design to your substrate. So lithography can be classified upon the methods of transferring the patterns or the sources which we use for the lithography. So just suppose if we are using X-ray beams for the lithography or transferring the pattern, so it will be called as X-ray lithography. If we are using electron beams, then it will be called as a electron beam lithography. If you are using UV rays, then it will be called as a optical lithography or UV lithography process. So currently we have the facility of UV lithography or electron beam lithography. So in these facilities we have mask writer tools, mask aligner tools, electron beam lithography tools and nano imprint lithography tools. So what is resist? So resist is just an organic polymer chemical. So resist is basically an organic polymer which acts as an intermediate layer over the substrate. So basically the resist chemical is sensitive to the source which we use to transfer our patterns. So if the resist is sensitive to the UV lights, then it is called optical resist, and if it's sensitive to the electron beams, then it is called as EBL resist or electron beam resist. So again we can classify the resist on the type of their chemical composition change after the reaction with the source. So just suppose if the resist is changing its structure after the exposure and it's getting solidified in the exposed area, so it's called a negative resist. So after exposure it will get hard from that specific area. If the resist is getting softened or it's coming out with the developer in the exposed region, then it's called as a positive resist. So how a negative and positive resist will be look like after the process. So as you can see, we have a resist layer over this substrate, this one, and when we do the exposure, so upon the type of the resist, if we are exposing this green part here, so this will stay if it's a negative resist. If the exposed area is getting away from this area, that means it's getting developed, so that means it's a positive resist. So in positive resist, basically the exposed area will come out in the developer solution, and in the negative resist the exposed area will stay there. Now for optical lithography, we have two direct writer tools. So both are from Heidelberg. One is 501 and one is 101 tool. So basically we can fabricate, we can write over a photo mask by using these mask writers. So MUPG 501 is having 390 nanometer wavelength, and MUPG 101 is having 375 nanometer wavelength. So after that we have a photo mask. So how a photo mask is made up of, like basically it's a soda lime glass over which we have chrome metal, and top of that we have resist chemical. So that's a full system which we call as a photo mask. So again as you can see, this is the base thing which we call as a soda lime. On the top we have chrome metal, and then we have resist. This resist is basically which we are getting, it's AZ1518, and the resist thickness is almost 500 nanometers. So how can we fabricate a photo mask? So first we have to decide the design, then we have to decide the layout. So at a specific area we have to expose our designs according to the requirement. So after exposing the design, it will look something like this. So after removal of the patterns which we have exposed, because AZ1518 is a positive resist, so it will look something like this. So when we etch the chrome in the open area, so here some areas are covered with the resist, so that will protect the chrome which is beneath that resist, and other area is open to open for the reaction, so that area will come out in the chrome etchet. So after the chrome removal, this is the cross section view of the photo mask. So now after photomask fabrication, so this is a basic thing, like a photomask will be having a different regions basically. So the central part of the photomask will be called as a utilized area, or I should say the useful area, which we use for the aligning and the pattern transferring. The next area is the mask area, where we can put some labels or notations according to our requirement. And the last part of the mask is the dead area basically, so that we use to get some support while using it in the mask aligners. So again, we can divide the photo mask in two types. One is dark field and one is bright field. So by the name you can take a guess, like it's dark field, that means the field is dark, and the bright field means the field is bright. So what does it means? The field is dark, that means the field other area than the design. So except the design, other area will be opaque, that means it's dark. So in bright field, the field will be bright, that means transparent, and in dark field, the field will be dark, that means it will be opaque. So the transparent area will allow the UV to pass through the photomask, and it will expose the wafer in the same region. Aligning the layers basically, that is also an important part. So just suppose if you have a number of layers in your specific device, so you will be aligning the first layer with respect to 2 and the third layer with respect to 2 and all. So again, to align the device layers, you need some reference points. So basically we will be using these alignment markers as a reference point. So if you can see here, we have this alignment markers on the top, and we have these alignment markers on the bottom. Just suppose this is our first layer design for the device. So and we want to align this second layer of the device with respect to the first layer. So we want that these vertical lines should just come above this first layer in the central region. So how can we do that? So first we have to prepare the design in the same manner. So in the design, it can be noticeable that both of the layers will be aligning to each other. But while doing the process, it's very important to do the alignment properly. So in that case, we will be using alignment markers. So when we will be aligning these alignment markers with these alignment markers while doing the process, we will know that the device will also align, because they are almost having at some specific location with respect to these alignment markers. So in the next slide you will understand. Yeah, so here if you can see, these alignment markers are aligned properly, and with respect to these alignment markers also, these devices are also aligned. So in first layer and in second layer, in both layer you will be having alignment markers. When you will do the process, you have to align the layer 1 with respect to the layer 2 by using alignment markers. Again, so you have to label the alignment markers, and that's also an important step basically. So in case if you have different dies, so you will be knowing like which die you are going to align now. So you can label your alignment markers with some specific kind of numbers or some notations. Again, so how many alignment markers basically do you need, and what should be the position of those alignment markers? So in case if you are having just suppose one alignment marker, so that is not sufficient to align the design with the previous design. So if you are having, just suppose you are having two alignment markers and both are at the boundary regions, so again there will be a chance of little misalignment. So at least it's suggestible to use two or more than two alignment markers at maximum distance to get the better alignment accuracy, or to reduce the theta misalignment. Yeah, so the process looks easier. As you can see, there will always be a critical link. Here in this process we have a critical link which is called mask or photo mask. So it is very important to select the photo mask precisely or properly. Which design you are going to fabricate on your photo mask, it plays a very crucial role. So again, it depends upon the next process. Just suppose your next process is etching, so you want some specific area to be open. If your next process is lift off, so you have to make some other area as an open area. So again, it depends upon the post process. So depending upon that, and depending upon the type of resist which you will use, so you have to make the design for your photo mask. So just for example, this is a photo mask design, and again whatever designs you are making, so we are generally accepting GDS2 and CIF format, because in Heidelberg tool we are mostly working with GDS2 and CIF files, because we are able to convert only these two files majorly. So in case if you are submitting any design, we will suggest you to send the design in GDS2 or .cif format. So design softwares which we are using to make the designs are K-Layout and Clevin majorly. You can use some other softwares also like L-Edit or Conventor, but the thing is the format should be in GDS or CIF. Again, there is a thing that the colored area will be transparent in your photo mask. Why? Because the colored area will get the exposure from the direct writer tool, and again after getting exposure this part will come out, and from here the chrome etching will start. So when we had our photo mask earlier like this, so after making a design, when we will expose this design, it will look something like this, because as you are able to see, the colored part, it got the exposure, and whatever we have the white region, it stayed there as in the form of chrome, so it's still opaque. So these are some basic guidelines or information which we have to share with you. Basically a process will go through a certain critical points and limits, so we should always take care of these points. So the first point is the mask which you are fabricating. So it is suggestible to go beyond or 3 micrometer feature at least as a line width or a spacing. Again, the colored area will get the exposure. So as I mentioned earlier, here you can see the whatever the colored area is there, it is getting exposed, and the white area will stay there as it is. Yeah, so point number 1 is clear, second is clear. The third one, it is always recommended to have an edge exclusion of 3 mm minimum. So just suppose if you are willing to go with a 4-inch wafer, so we are suggesting to keep at least a 3 mm of area inclusion, edge inclusion from the boundary basically. Why? Because there might be some edge bead formation during the spin coating. Also, if we are going for etching or DRI processes, so again the edge part will get affected. So the devices which you have on the edges, it will get affected for sure by the process. So you cannot use those devices for the characterization or for your further processes. The next point is, it's generally easier to draw the structure first and work on the polarity afterwards. So yeah, in case if you just suppose if you want to fabricate this device, but now you want this colored area to stay there on photomask, or you want this colored area to be opaque. So how can we do that? So we have to change the polarity of this design. So first, like once if your design is ready, then you can later on change the polarity of your design. That's up to your requirement basically. So once if your design is ready, we can later on change the polarity by using different functions, XOR or inversion. So if we are inverting this design, or if we are going for XOR for this design, then basically what will happen, this white region will become the colored, or this colored region will become the white. It will basically invert the polarity of the design. Or next point, for very fine alignment, process quality and monitoring, simple alignment markers will not suffice. It is recommended to use the standard alignment markers. So we have some standard alignment markers which is having vernier scales and some other small and big plus structure cross and other kind of like different alignment markers. So basically it is designed for better accuracy or precise lithography process. So we are suggesting to use only those alignment markers. And standard alignment markers of analysis should be used. Yes, as I mentioned earlier, layer to layer tolerance of 2 micrometers should be included in the design to take care of process variations after litho etch process. Yes, so there will always be some room for the errors during the process. The process will not be 100% ideal, but So but there will always be a chance of minute error. So keeping that in mind, we should always like at least keep 2 micrometer of tolerance in the alignment, because again if we are going for just suppose 6 or 7 layers of alignment, so there might be just suppose 250 nanometer alignment misalignment in first and second layer. Again that misalignment will affect the third layer alignment. Again that misalignment might affect the etching, dry etching or wet etching process. So again the overall misalignment will be there. So keeping that in mind, we are recommending to keep at least of 2 micrometer alignment tolerance. So the next one is zoom into the design to check the connections in the design device, open gaps and shorts, etc. So again this is a very important point, because sometimes like what happens when you fabricate your device design in the software. So after designing there might be some voids or some extra lines, because we are using a lot of operation in our devices geometries. So basically just suppose if you want to like make some device, you are using 3 or 4 different kind of geometries and you are applying some operation XOR or anything. So after operation there might be some like line residue or some void creation. So you have to zoom in and check your design whether the design is fine or not, because that might affect your process and that will replicate in the further processes. So these are some images from the optical lithography. Now the mask aligners. So what is mask aligning basically? So in mask aligning basically we will be using a photo mask which will be having an opaque region as well as a transparent region. So the transparent region will allow the UV to pass through it, and that will expose the photoresist over the substrate in that specific area. So we have the sources of 365 nanometer and 250 nanometer deep UV, and the positive resist which we are using is AZ series and S series, S1813, AZ5214 and AZ4562. Then in negative resist we have AZ Unlock 2020, 2070 and SU8 series. So when we are using a photo mask, the transparent part will allow the UV and the opaque part will block the UV to expose your sample from that specific area. Now, so what is the process flow for the photolithography? So basically first we will go for the wafer cleaning. Okay, so after wafer cleaning we have to go for dehydration bake. So for wafer cleaning we can either go for Piranha RC or any solvent cleaning also. For dehydration bake, basically we are heating the substrate on a hot plate or oven just to remove the water contents from the substrate. Then we have to go for spin coating. So basically we are spin coating the resist chemical which will act as an intermediate layer. Then we have to soft bake the full substrate with the resist, so that we can make it ready for the further step which is exposure. Then we have to do UV exposure. Then it's time for development. So in development basically we are removing the exposed area if we talk about the positive resist, and we are removing the other area rather than the exposed one if we are using a negative resist. Then hard bake. So it's optional basically if we are going for etching. So etching basically if we are removing the metal or the oxide or the silicon, if we are etching it, then we need a hard bake, or else if we are going for a lift off process, then we don't require a hard bake basically. We have a mask aligners EVG620 NT tool. So these are the tool specification. It's having a 365 nanometer UV source, and for DUV we have 248 nanometer wavelength. And we have one more mask aligner tool, MJB4 tool, and this is having same 365 nanometer normal UV. So here also we have different modes of exposure: soft contact, hard contact, vacuum contact, low vacuum and gap exposure. So also we have a standard quartz mask. So by using this standard quartz mask, we are able to achieve 1 micron and 2 micrometer features over the resist, and whatever the smallest feature it's having like 0.6 micrometer, it can be patterned by using a positive as well as the negative resist, so that will come into the DUV process. And this is the top side alignment accuracy in the MJB4 tool. So it's almost equal to 1 micrometer. And we can use this optical lithography process or these mask aligners for different kind of applications. In case if you want to make some micro pillars or micro pyramids, or if you are going for bilayer profile, so these are some images, and this image is after dry etching process, so you are able to see this pillar. Yeah. So we also have AVG 501 wafer bonder tool, so which can be used for the wafer bonding process, just to get a hermetically sealed bonded wafer. So basically we can do fusion bonding, eutectic bonding, anodic bonding, and thermocompression bonding by using this tool. And this is the example for a sample which we have bonded using the EVG 501 bonder tool. And this one is the NIL tool, nano imprint lithography tool. So these are the tool specs. Then we have electron beam lithography. So basically what is electron beam lithography? So we are just focusing electron beams, and we are penetrating the resist layer over the substrate by using this electron beam, and then we are getting the patterns after the development. Again, it depends upon the type of resist which we are using. If it's a positive resist, the penetrated area will get the development, and the other area will stay there. For the negative resist, the exposed area will stay there, and the other area will get development. So for electron beam lithography, we have two tools, Wraith Pioneer and Wraith E-line. So both are 30 kV systems, and basically these both tools are having high resolution SEM in it, so we can inspect the top surface of a sample. And the Wraith E-line is having FBMS mode. So what are the steps in electron beam lithography? So basically the same thing, we have to clean the substrate first, then we have to spin coat the resist chemical, then we have to go for the exposure, then we have to go for the development. And like this we have to create a design for the electron beam lithography process. So this is an example of a GDS file. So generally what happens when we go for direct writing or a direct lithography process, so there might be chances that the line, if it's too long, it will not be regular. There might be some stitches or some variation in the alignment. So basically you can see here, this is a stitching error here. So to overcome this, we can go for fixed beam and moving stage. So here the beam will be fixed and the stage will move. So this can reduce the discontinuity, or I should say the stitching error in your sample. Now these are the EBL resist which we are using. So we have PMMA series, and for negative resist we have MAN series and HSQ, and developers we are using MIBK IPA and EZ MIF 726. So this is a like general comparison between EBL and UV lithography. So in EBL basically we are going for electron beam lithography, like we are using electron beams, and here we are using optical UV rays basically. So the thing is the resolution will be much better in electron beam lithography, because the spot size is very less comparable to UV, and the throughput, if we compare, then in EBL the throughput is very less, or I should say the number of samples which you can produce is very high in UV, because the writing speed, or I should say the lithography process timing, it is very less in optical lithography, whereas in electron beam lithography it is very high. So exposure method, here in EBL we are doing the exposure point by point, and here we are either going for a flood exposure by using a photo mask like a mediator, or we are going for direct writing which is giving a high writing speed. Then usage, so basically electron beam lithography majorly we are using for R&D and research purpose, and for optical mask production, which is having very critical features, sub-micron features. For UV lithography we are using those photo masks for bulk production. So these are some images of electron beam lithography. So that's all from the lithography team. Thank you.